Hey guys, welcome back. This is the first installment of a two-part series for the final video of the quarter. So I thought that you guys were going to finish up amino acids in lecture today, but looks like you guys only got through the acid-base stuff, which I think means that on Friday, you guys are going to cover the reactions or whatever you can in the time period you have. So that's okay. For your quiz on Friday, you'll need to know acid-base qualities, pK, stuff like that. So that's all that I'll worry about in this video. We can worry about reactions a little bit later. Just means that I can make two videos now that are shorter rather than one longer video. So that's something to look forward to. So this video is just going to cover amino acids and their structure, quality, acid-base stuff, things like that. Because of that, that probably means it's going to be a shorter video. So I'm going to aim for 30 minutes on this, no more than 40, just so it's very quick, something you can just 2 times and watch very quickly, just to kind of remind you and just to show you some tips and tricks to do that PK stuff a little bit faster, or at least have a better conceptual basis on that. Okay. Now, with that being said, right, we're in the final stretch here, right? This is, the very last thing we're going to cover, right, is amino acids, and we're finally going to be done on the way to, close this chapter of OChem in our lives. So let's try to close this out very nicely, and maybe have a great time doing so. Okay, let's make sure that hard work that you guys are putting in is paying off. Okay, cool. So with that, let's just get right into it. Amino acids, part 1. Okay, but amino acids, when we say amino acids, right, what do we really mean, right? What is it that we're conveying, right? Well, what we're saying is that we have a molecule that is amine and acid, right? It's part amine and a part acid. But one other thing that we're kind of whispering is a little bit in the front, right? Really what we mean is that these are alpha amino acids, okay? So what does that? Just means that we have on the alpha carbon of that carboxylic acid, the amino group, okay? But there's so many different types of amino acids. You can imagine like we have, again, all that really means is there's a carboxylic acid and amine. So, this would be an amino acid. What is this? Alpha, beta, delta, or gamma, delta. So delta amino acid. You can imagine something even longer, like I guess this would be like an epsilon amino acid, right? Alpha, beta, gamma, delta, epsilon, whatever's after epsilon, I don't know. Maybe something shorter, like a beta amino acid, but there's so many different types of amino acids in the world. Mainly when we say amino acid, we're talking about the alpha amino acids or the essential amino acids, the ones that are important for human biology and biochemistry, right? The amino acids that make up our own body, right? So our main thing I try to understand today is how alpha amino acids work, their chemical makeup and their structure, stuff like that. Because these guys are what are relevant to our biochemistry. Okay? So yeah, that's going to be the focus of today. Now, this here is a biomolecule, so I'm so interested in it, and particularly, right? What do these guys do? Take a couple million of them, you couple them together, and what you get out are these peptide chains, right? So you take a bunch of amino acids, you put them together, what you get are peptide chains, and these peptide chains make up proteins. Okay, so these are what are making up our proteins here. And proteins, so incredibly important, right? Proteins make up our structure, our scaffolding, our support. They are the reason why we are here today as humans, right? They're so wildly important. So it's really important that we understand them, right? Shout out to the amide bond, right? That's what we talked about in the last video, right? Why is it that it's so important that amides are so resilient to absolutely everything? Why isn't that they don't just give up when they see a water droplet, right? It's because they're so strong and they're making up our entire body, right? They're making up our proteins. So shout out to the amide, right? Okay, cool. So this amino acid here in particular, the one I've drawn, right, where we have 2 hydrogens here, this is glycine. Okay, and so because there's 2 hydrogens, this is a achiral amino acid. Okay, but a majority of amino acids are chiral. And so if I were to kind of draw a generic amino acid, oops, kind of messed it up. There we go. Right. Majority of them look something like this. The chiral ones, they look something like this. And so if I were to kind of assign stereochemistry, amine is usually 1, carboxylic acid is usually 2, and then R is usually 3. So that looks like a clockwise line, but because H is in the front here, it's actually going to be the opposite. It's a counterclock line. And so if it's counterclock, that means that this here is an S stereocenter. Okay, so majority of amino acids are S amino acids. And if you remember with sugars, right, sugars we had an S stereocenter, we had what we called it a left-facing OH, right? So here we have L-glyceraldehyde, right, which had a S stereocenter. And so because the S stereocenter, we called it an L sugar. Well, same thing with amino acids, right? Just got to replace a couple things, right? Like replace the aldehyde with a carboxylic acid, replace the hydroxy with an amino, and then the CH2OH we just replaced with R. And now we have an S amino acid in a Fischer projection, and we call this an L amino acid. Yeah, so our amino acids are L. They all follow this build, and a majority of them are S. Now, glycine, right? It's achiral, so obviously it's not going to be chiral at all. It's technically not an L amino acid. It's not chiral, but we do have another amino acid that is L that does kind of fit the bill, and that is going to be cysteine. Okay, so what's so special about cysteine? Well, cysteine, if you want to really quickly do it, actually does not follow our stereochemical rules. Instead of carboxylic acid being 2, it's actually the sulfur. And so that kind of that turns our spin around. So actually it is an R amino acid, but that's okay. Being R doesn't really change anything, right? That's just a naming convention we have based on, that's just a naming convention we have based on based on weight of an atom. So it's just completely by like accident that it's not S, but it's still considered an L amino acid, right? Because the configuration hasn't changed, as in how it looks hasn't changed. It looks like every other single chiral amino acid, and that it has like a build like this one. So still consider it an L amino acid, just it's an R stereocenter. So it's like a note card thing that I would write down. Okay, cool. So that's kind of like the nomenclature, how we get around naming these guys, and what a majority of them are. Okay, but if I had an amino acid, right, in solution, right, we talked about this in the last video too, right? We have a carboxylic acid, which is an acidic moiety, and we also have an amine, which is a basic moiety. And like we talked about last video, amines and carboxylic acids interact with each other, right? Specifically in that amines deprotonate carboxylic acids. So it's actually incorrect to draw an amino acid that's neutral with no charge. The more correct representation of this is actually carboxylic acid that's deprotonated as a carboxylate and an amine group that's protonated as an ammonium. And so this neutral amino acid that we see here, that's neutral by charge, is what we call a Zwitter ion. Now, Zwitter ions, the term Zwitter ion kind of gets thrown around a lot. Like we'll refer to it. I mean, I will probably refer to it a lot. Like I'll use that term just to describe any kind of amino acid that's charged. But generally speaking, when we think of Zwitter ions, what we're talking about are the amino acid when it's in the form that's neutral, right? A majority of amino acids, their only ionization states are going to be the plus and the minus on the carboxylic acid and the amine. But we have about 5 amino acids that have R groups that can also ionize. And sometimes I will do it, other people will do it. We kind of refer to all those forms as Zwitter ions. Now, again, outside of a classroom context, it really doesn't matter. But because your class really cares about vocab and getting that term right, I believe the correct usage of Zwitter ion is really when we have a neutral charge. So it's only correct to call this amino acid form here the Zwitter ion, although it's very likely that people will refer to every form of an amino acid as a Zwitter ion. So just to kind of get that vocab stuff out there right now. Okay, so I apologize if I do that myself. It's just kind of a very like knee-jerk thing to do. Okay, but again, this is our Zwitter ion, right? Amino acids are always going to be charged because they have acidic and basic moieties. So whether we're in acidic or basic condition, right, the dominant form of amino acid can change. For example, I mean, obviously at neutral, we have a positive and a minus, right, neutralizing each other out. But suppose we have a form that's more basic or a form where we have no protons. that would be a form like this one. So this would be our basic form, or quite the opposite, right? We have a form that is full of proton, that is completely protonated. Okay, and that would be this here. So a majority of our amino acids, again, about like 15 of them, share these three common ionic forms of the amino acid, right? The acidic form that is completely protonated at every position, the amine and the carboxylic acid. The basic form, which is completely deprotonated at the amine and the acid, and the neutral form, which again is just one deprotonation, one protonation, right? So these are our three dominant forms. Now, again, amino acids, we usually deal with these in buffers or in biological systems that are usually, dictated by pH. And so it's important to know at which pHs, right, we will expect to see which dominant form, right? Like, I mean, if you think about just biochemistry, if you're doing some kind of test, or if you're trying to do some kind of reaction at some particular part of this molecule, it's important to know what charge state your amino acid molecule is in. So we use very empirical values to dictate when a particular group will be ionized or won't be ionized. And those values are pKa, right? So pKa, that helps us determine when a group should ionize and when it shouldn't. Now, again, majority of amino acids that only have ionizable groups on the alpha amino and the alpha carboxylic acid, right? The pK values that we see for these guys. I'll use about rough values here. Like I know there's like, it's like they're decimals, like technically this should be like 2.7 or something, but I'm just going to round down to 2 just to make our life easier. And same thing with the amine, I'm just going to call this 9, right? Just to make our lives easier. Okay. But these pK values tell us at which pHs we should expect 50% deprotonation of the carboxylic acid or 50% protonation of the amine. So when I look at these different states here, right? I mean, generally, you can kind of assign it, right? 2 is sort of the acidic pH value. So 2 would go on this arrow, and 9 is the basic pK value, which would go here. And you can kind of see how that dictates it, right? At 2 is where we have the switch between the carboxylic acid and the carboxylate, versus 9 is where we have the switch between the ammonium and the ammonia. Okay. So for those who don't remember, which is totally fine, it's been a long time since you guys have talked about pKa, right? What is pKa? What does it mean? Well, pKa is a value that tells us at which pH we expect to see 50% of a protonated and a deprotonated form, right? So it's sort of telling it when you have 50% ionization and 50% deionization, I guess. So ionization versus not ionized, right? So here, this is not ionized, but this is ionized. And at a pH of 2, these would be about equal, right? 50%. Right? Same thing with this here at 9, right? 50% ionized and then 50% unionized or not ionized. And that's what the pKa value means, right? So it's when we have equal amounts of both forms. Now, whether you move up or down from the pKa on the pH scale will determine whether you have a dominance of one form over the other. So for example, if I'm at pH of 9, right, obviously I have 50% of this and 50% of that. But if I go down to like pH of 5, I'm going to slowly start to increase the dominance of this form here. Same thing with this, but on the other side, right? If I creep up to a pH of 13, I am slowly increasing the concentration of this form here, right? And you can apply the same logic with the group over here, right? Whether the carboxylic acid or the carboxylate is dominant will depend on whether you have a lower than 2 pH or a higher than 2 pH, okay? Now, to kind of help you guys summarize this to make it a lot easier, right, to determine, which pHs, what do they mean for every pKa, I've sort of come up with this little trick, this little rule that we can use. And it can really help you out in determining dominant form or dominant Zoeter ion at a certain pH. But if we treat pKa as sort of the equal point, right, as sort of the 50-50 point between, which form is dominant, then every pKa, or sorry, every pH above pKa, right, we can think of as a basic pH. So that means that, for example, at 2, right, every pH above 2 is a basic pH for the carboxylic acid group. That means that the basic form is what's going to be dominant at pHs above 2. And we can see that, right? Any pH above 2, we have a dominance, sorry, not the whole thing, but we have a dominance of that carboxylate form. Every pH below 2, and suddenly we have a dominance of the acid form, right? Because again, if we think of it as a neutral point, going below the neutral point is acidic, going above the neutral point is basic. Okay, so I like this better than the whole pH above or below, because I hate having to memorize things like that. It's just easier for me to remember, qualitatively. Oh, hey, I know that above a neutral point is basic, below a neutral point is acidic. So it's easier for me to remember, okay, if a pKa is in the neutral point for a group, right, then the dominant group will be just based on whether we're below it, so acidic, or above it, which is basic. Okay, and so you can use that, and we'll do a couple problems after this where we kind of predict the dominant form of an amino acid, and we'll use this rule or this little trick to help us figure things out a lot easier. Okay. Now, one last thing before we get into the acidic and basic amino acids and their dominant forms, right? The neutral amino acid, right, the one that we see here, right? There is a point at which there is 100% of neutral amino acid, and that can be something important that you want to know for whatever reason. To kind of conceptualize this, right, 50% of the neutral form is at 2, and 50% of it is at 9. So if I wanted to increase this all the way to 100, you can imagine there's a midpoint here. Right, so there's a midpoint here at which we have 100% of the neutral amino acid. This point we call the pi, and again, it's in the middle of 2 and 9. So for a majority of amino acids, about 15 out of 20 of them, the pi is 2 plus 9 over 2, right? The midpoint formula, which is 11 over 2, which is about 5.5. Okay, so around about 5.5. That's the p. That is the pi at which we have a dominant neutral form. Okay. Now, again, for amino acids that have just some random R group, or if they're glycine, right? That's just what's going to be the case there. Okay. Now, what happens when we throw an extra group in the mix, right? Like, let's say our R group has an acidic quality or a basic quality. Things get a little trickier, but not too much trickier. Okay. So let's, for example, say we had an acidic group. So actually, I guess I'll draw it up here first. 1, 2, okay, there we go. So let's say we had an acidic amino acid. This here is glutamic acid, right? That should be glutamic acid, I believe. Yeah, glutamic acid. Okay, and if we look at the R group, we have an acidic moiety, or maybe we have another carboxylic acid, so it's going to be a little more acidic. So we could devise some ionization states for this guy. Okay. The easiest way to do this, if you want to do this or how to do this, is you can start with the most acidic, everything protonated, and then slowly lose a proton. If you're having a hard time determining which proton to lose, that's totally fine. It helps to know the pKa's. So for example, pKa of this, again, we're going to say is about 9. This is about 2, and then we'll call this one 3, just for the sake of the, just for the sake of it. And then just arrange this from lowest to highest. Okay. Remember, 2 controls the midpoint between the ionization of this carboxylic acid. So the left side should be acidic form, so the OH. The right side should be the basic form, so it should be O- here. Okay. And then we have 3, which is going to control, right, this guy down here. Right, that's formed now. So acidic is to the left of 3, basic is to the right of 3. And then nine, right? Which again could apply the same theory, right? Acidic and basic on either side. Okay, so these are our amino acid pseudoionic forms for when we have an acidic group. Now, when we look at these pKa's, right? Or these, sorry, these the pseudoionic forms, you'll notice that this third charge, right, kind of makes things a little more complicated, right, in terms of finding that neutral form, because now we have another minus charge to deal with. That's totally fine, right? I mean, there's minus minus, so -2, minus minus plus, so -1. Here's our neutral point, and here is our +1. So our neutral point for an acidic amino acid is going to be lower than what we normally expect, right? Because before it was between 2 and 9, or like, I mean, this is about the same. So it's like technically around here, but introduction of that acidic group brought down the pi, right? Or brought down the neutral form. So now it's going to be here, the pi, right? Our neutral form is going to be the midpoint of these two numbers. So acidic PIs, right, tend to be lower than neutral PIs. Okay, so 2 + 3 / 2, that's going to be 5 / 2, which is about 2.5, okay, which is brought lower. Okay, here's a cool little trick. There's 2 amino acids that are acidic that you need to know, and both of them have carboxylic acids. That's great. This is aspartic acid. Okay, so if you see an R group with a carboxylic acid as the R group, you know you want to take the average of the two lowest numbers for pi. That's great, right? Very, very simple to remember. Okay. Now, again, if you wanted to predict a dominant pseudoionic form, I mean, if you have them drawn out, it's fairly simple, right? Just kind of plot out which one is. But like, for example, let's say we wanted to know the dominant pseudoionic form at a pH of like 13, right? I mean, if you have it drawn out, you can kind of quickly look there and do that, right? And say, oh, 13 is here, so this is the dominant pseudoionic form. But what can you do if you don't have that, right? If you don't have all these drawn out, or you don't have the time, it's very, very simple, right? We can use our little rule where pKa, if your pH is to the right of it, it's basic form. pH to the left of it is acidic form. Okay, so this is what we can do. Let's say you're asked, what is the dominant pseudoionic form? Let's say you forgot these, or you don't have that, right? But let's say you're asked, what is the dominant pseudoionic form at a pH of 7? Okay, how can we quickly predict what is going to be the dominant form if I don't know these numbers, or if like I don't have all these drawn out? Very simple. Let's go ahead and draw out our amino acid just in general. So I have it drawn out. And again, pH of 7, right? We just want to compare that to the pKa. So we can start with the carboxylic acid on the right here, right? But again, that's going to be a pKa of 2. And 7 plotted against this is going to be on the right of it, so the basic form. So our carboxylic acid should be basic, it should be O-. Okay, move on to 3 here, can place 3 here. Again, 7 is to the right of that, so great. That means that our R group is going to be minus as well, right? When I plot 9 against this though, right, 7 is actually to the left of 9. So over here, so now it's in a acidic form. So this is going to be our acidic form here. Okay. So you don't even have to really draw out all the forms, although it can help you with PI, for example. If you're just predicting the dominant form of an amino acid, by all means, just use this quick trick, right? We got this done in less than a minute, able to completely predict what is the dominant form. And we can see here when I put back the numbers, right? 7 does fall here, and these match perfectly. So that's great, right? We love a trick that works, don't we? Okay. So again, acidic amino acids introduce an acidic group, usually a carboxylic acid, right? So that's what makes it an acidic amino acid. And 2 amino acids of our 20 that we need to know, or just to know that there are, I think there's like 20 of them. They are acidic and they have carboxylic acids. So very easy to tell, very easy to give away. Now let's say that I have a basic amino acid. Okay. So the one that I can remember is alpha, beta, delta, gamma. Wait, alpha, beta, delta, gamma, epsilon? I think it's epsilon. Okay, but this here is lysine. Okay, it's acidic amino acid. Maybe you guys are starting to notice a trend here, right? The acidic amino acids had 2 carboxylic acids. Basic amino acids tend to have 2 amines on them. So that's pretty cool, right? That's great. That's nice to see. But again, if I had to give these values, this is about 9, 2, and this is about 11 here. Okay, so if I wanted to, I could draw all the all the forms possible. Okay, so that's something I can do. right? So the most acidic form, and then again, we'll slowly lose a proton. This will be 2. This will be 9. And then this here will be 11. Okay, and so you can see here we have a completely basic form here. Okay, so now again, it might be a little confusing, but we can still figure out the PI from this. Just look for the neutral form. I mean, this is -1, this is 0, so this is where it is. And as you can see, our PI has shifted up, right? It's now higher. Again, it used to be between 2 and 9 in the neutral form, but now it's going to be between 9 and 11. Okay, so kind of interesting there. We take the average of that, right? 9 plus 11, right, over 2. This is going to be 20 over 2. It's around 10. It's around 10. Okay. Again, I'm using values that are just kind of rough just for the point of doing this. But if I have a basic amino acid, right, you take the 2 highest pKa and you average them, and that is your PI. Okay, so that's our neutral point if we need to know it for whatever reason. Okay. Now again, for PI, drawing these out is very useful. And if you have drawn them out and you're asked about for dominant form, you can also just very quickly figure that out too. Like if I asked, where on these, what would be the dominant form at like 8 or 7 or 1, pretty simple to figure out. But let's say that you're on a time crunch and you just got to solve something, right? This is something you can solve very easily. For example, let's say that you're asked, kind of move this stuff over for space. Not mean to do that. Okay, but let's say that you're told that you're at the pH of 0 for whatever reason. And you have to, or not 0, let's not do 0, let's do 7 again. Okay. And you're told to draw the dominant zwitterionic form, right? Again, I'm just going to use our little pKa rule, right? Which is that if I'm to the right, I am basic. If I'm to the left, I am acidic, right? And so we can start with maybe the mean group this time. So this is pK of 9. If I'm at a pH of 7, that's to the left. It's acidic form. So this guy is going to be NH3 plus. Right? If I'm at 11, that's still the case. That's to the left. So this is also going to be acidic form. And if I'm at 2, well, now 7's on the right side. So that's the basic form. So this is going to be O minus. So again, look at that in like less than a minute and 30 seconds. Right? You guys can do it even faster. Just got to do practice. We can completely determine what is the dominant zwitterionic form at any pH. And again, we can kind of plot these numbers back in. And we can see at pH of 7, which would be here, this is the dominant form, the plus plus minus form. Okay. So it can be really useful. I think this trick is really, really useful if you want to go and very quickly do any question about dominant zwitterionic form. Super, super fast, right? Doesn't take more than a minute. But for PI, right, it's usually safer to just quickly draw them out just to make sure you've done them correctly. I'll let you guys know right now, a majority of amino acids kind of follow the rules where if they're basic amino acids where they have an amine, then they should be the 2 highest average. If they're acidic, it should be the 2 lowest, and then the rest are just kind of like the 2 and the 9. I'm aware of 1 or 2 of them kind of being weird. I just can't remember which ones off the top of my head. I think it was... Man, there's one that's weird. I just can't remember. I apologize. There's one I know that's weird that doesn't follow it, but I can't remember it, but it's okay. Honestly, what I would do for you, if I were you guys, is just look at a PI table. There are, again, 2 acidics. So the acidic amino acids are glutamic acid and aspartic acid. And then the basics, there are 3 of them. One of them we just looked at, lysine. There's histidine, and then there's arginine. Okay, so these are the guys that if you want to use the 2 high or the 2 low, right? 2 highest or 2 lowest pKa's. This is the one that always works for PIs for these 5. And then the rest should follow that it's just 2 plus 9, like the 2 plus 9 divided by 2, right? Something rough to that. I'm just aware that there's one of them that's a little bit weirder. Actually, you know what? I'm saying the stuff. Let me just look at it right now. So PI chart. See, Google's been talking about pi. PI amino acid chart. Nope. I don't know what to do there. University of Calgary. Let's see what you have to tell me. Yeah, so majorities are around 6. The one that fails this is, who is it that fails? Man, it's kind of hard to tell. They're all kind of the same. Oh, cysteine. Cysteine fails. I think it's cysteine, is it? Ugh, I can't tell. Okay, well, whatever. Maybe just forget that I said that. I think I'm just confusing myself on that. But anyways, majority of our amino acids should follow the rules that we just talked about for PI. Okay, cool. So that's all the pKa nonsense, all those shenanigans there, right? Again, a majority of amino acids are just these 3 here, right? Because they don't have an ionizable group, right? They just have some random R group that just hangs out. So majority of them are acidic, neutral, and basic. And again, if you want to determine where these guys are, like in terms of dominant form, you can do so just by either plotting them these 3 out very quickly in 2 and 9, and seeing where they are, or just using our trick, right? Our little trick on using pKa and acidics being to the left and basics being to the right. Okay. And again, the PI for these is usually around 5.5, 6-ish, usually, right? If we have an acidic amino acid, right, PI is a little bit lower. There's 2 of these, glutamic and aspartic acid, right? Basics, we have lysine, we have histidine and arginine, which I guess I'll just draw them just for the sake of drawing them so you guys can see them. I think that it doesn't hurt to just see these guys. By the way, I know you guys don't have to memorize your amino acids for this class, but it is good just to know them because you never really know. This one I always mess up on. It's good to just know them, in my opinion, at least. That should be histidine. I think I drew that one correctly. I'm going to believe myself that I drew that one correctly. But this here is histidine. This is the lone pair that protonates for histidine, if you were to protonate it. And then arginine looks kind of like lysine, but it has this like weird feature in it. Let me draw this a little bit clearer. Alpha, beta, delta, gamma, epsilon. Was arginine shorter or longer? I think it might have been shorter, actually. I think it might be a little bit shorter, but it's okay, whatever. I'm not a biochemist by any means, but this here is arginine. And again, kind of, you can see the kind of feature, right? They all have nitrogens in them. So these are your 3 basics. So these are the guys, if you want to use the PI rules, right? That's the ones you would use, like glutamic, aspartic, lysine, histidine, arginine. But again, the rest of these guys, so glycine, alanine, serine, all those guys out there, gonna follow just the pattern that we see back here. Okay, cool. All right, so hopefully that helps you guys out on the PI side of things. Okay, all that's really left now is just understanding protein structure, how amino acids kind of come together to make protein structures. But again, amino acids condense together. So let's say I have an amino acid here, an amino acid here, right? All you're really doing, oops, this is meant to be a nitrogen. All you're really doing is condensing these 2 sides together, joining them together to make a peptide bond. And out you get is a peptide. So the simplest peptide you can call a dipeptide, just 2 amino acids put together. And you can imagine, right, just the more peptides you put together, the more it becomes a polypeptide up until a protein. Usually proteins have like millions. I mean, we're talking millions of amino acids. I think Whenever they talk about sequencing proteins, I mean, those take decades because you're going through every single amino acid in a protein, right? So this here is what we call a dipeptide. You can imagine 3 of these would be a tripeptide. I don't know if we do anything after 4, but it's usually, I think it's like oligopeptides. So it's like di, then tri, then oligo, and then polypeptides, I think. Might be wrong about that. Again, I'm not a biochemist. But yeah, that is what a protein is. It's just a condensation between these two to form that peptide bond, that amide, that resilient bond, okay, that makes up all of our proteins. Okay. I believe you guys will learn one reaction to put these two together on Friday, which that'll be nice to learn. You would do this just with a DCC. That's the synthetic way of doing it. Okay. But again, the peptide bond, that's sort of the major primary structure. So when we talk about amino acids and proteins, we have different types of structures that we can refer to. When we talk about primary structure of a peptide, we're talking about the amide bond. So particularly this here is our primary structure. So primary structure is just how our individual amino acids sort of linked together. That is our peptide bond there. When we look at how that how that peptide amide interacts with itself, right, via intermolecular interactions. So you can imagine hydrogen bonds between different backbone components, right? That is what we call secondary structure. Okay, so the amide bond makes up the primary structure. How the amides interact with each other via intramolecular H bonds. So backbone H bonds, that is secondary structure. These are those alpha helices and those beta pleated sheets that you guys hear about all the time. So if I have an alpha helices, right, the interaction that's holding this together is the nitrogen and the carbonyl of the backbone amid hydrogen bonding with each other. Cool little thing. So when you get into biochem, you'll learn about what's allowed and what's disallowed in these kind of structures. And one really important thing is that, I mean, these coils, right, they need to be able to turn, right? They need to be able to have flexibility. So there are certain amino acids that are just not allowed in these kind of turns. You need something with a high level of rotational freedom. One of the best amino acids you can see at a kink or at a turn is glycine. Because glycine literally has no bulk. It has complete rotation, or at least it has a very a lot of it's free of consequence of rotation. So you usually find a lot of glycines in there. One amino acid that's a little unforgiving to put into a helix is a proline. So proline, kind of an interesting amino acid because it is a 5-membered ring. Right? Oops, did I draw that wrong? There we go. That should be proline. Right? Yeah, that should be proline. And so proline, because of its ring, is very unforgiving in being placed inside of these coils. If anything, you get these like very unnatural turns and twists, or like a really hard like kink in it. And it's like, oh, that's a proline that's in there. Okay, so cool little biochem tips, maybe things that you guys are a little more interested in. But alpha helices are secondary structures because they are built and supported by amide backbone interactions. Beta pleated sheets, that's probably something else you guys have heard of, but again, that's also backbone interaction. That's what we have there. Once we've looked at the backbone, right, and what interactions it has, we can then ask, what about the R groups, right? What about our acidic and basic and normal R groups? Well, there's actually a lot of types of R groups, right? I mean, we've talked about today acidic and basic, right? And so these guys can make what we call salt bridges, right? Because we can have a minus group and a positive group kind of bridge together in an ionic interaction. Right? These guys can have an ionic interaction that brings the peptide together close. But we can also have other kinds of R groups. For example, we can have aromatic R groups. Okay. And aromatic R groups are like tryptophan, phenylalanine. So this is phenylalanine. We can have tryptophan, which is a indole type. Right. What's the last one? There's tryptophan, there's phenylalanine, and then tyrosine. Okay, how did I forget? And so tyrosines are like the aromatic R groups. These guys are interesting. They do something called pi stacking. And so what pi stacking is it's interaction between the rings of aromatics where they kind of stack on each other. Now, kind of a tangent, but for the longest time, people thought that aromatics were pi stacking like dinner plates, which doesn't really make sense because remember, in organic chemistry, the minus wants to float over the positive or they want to interact with the positive. So for the longest time, people were like, for some reason, saying that if there's a pi stacking interaction, they have to be like dinner plates, like right over each other. But that makes no sense because you are overlapping electrons over each other. So slowly and slowly, people start to realize, oh, actually, there's two types of pi stacking interactions. There's a perpendicular interaction. Right, so there is a interaction where they are perpendicular to each other, kind of like this, like, kind of like an L, right? Kind of like an L. And then there's another one where they're kind of just offset, right? So they're not directly stacked to each other, but they're just kind of stacked to each other. So cool little thing there. A lot of biochemists were just kind of not thinking in those interactions, but there's aromatic R groups, right? And those guys can have pi interactions that can bring or open up a ring, a protein. There are hydrophobic aromatics, hydrophobic R groups. So alanines, leucines, isoleucines, stuff like that. Usually carbon groups. And these guys are interesting. They form what we call hydrophobic pockets, right? Because think about it, the biological system is an aqueous system, right? It's very water, or it's very like, polar. And so these hydrophobic amino acids with their R groups, what they'll do is they're kind of like curl in, like the amino acids will kind of curl them in, kind of protect them from the aqueous environment. And so these guys can be responsible for sort of like interesting pockets that form because the amino acid kind of curls in on itself to kind of protect these, carbon-based amino acids. Like if these are the R groups here, kind of curls in to protect it from the rest of the environment. So it makes these like, hydrophobic pockets. Right? On the other hand, we can have hydrophilic amino acids. And again, these are guys that are, they're very willing to interact with the environment. So you're thinking like serine, possibly even cysteine. Speaking of cysteine, cysteine can make bridges. So if I have two cysteines, cysteines can actually make bridges with each other. We call these disulfide bridges. And this is an excellent example of a tertiary structure. Right. Oh, I don't know if I mentioned that this is tertiary structures, by the way, when we look at it, the R group interactions. So disulfide interactions, cool little bridges that when you're doing peptide analysis, you actually have to account for this because if you don't, then you're going to have, peptide chains that are stuck to each other, peptides or amino acids that are still stuck to each other because of these disulfide interactions. Okay, cool. So I think I've been ranting a little bit and I didn't want to do that. Hopefully I haven't taken too much time, but that should be about it. That's all I think you really need to cover. But yeah, that's going to be the qualities of amino acids. Hopefully this was helpful. You guys learned something. If any questions, please let me know. Yeah, cool. All right. Well, you guys have a night. See ya.